new generation telescopes, engineering landmarks in space and on the ground have opened a whole new window onto the far corners of the cosmos. They are capturing photons from the deepest regions of space, bearing witness to an extraordinary chain of events that launched our universe over 13 billion years ago, at the brink of the cosmic dawn.
T-minus 30 seconds and counting.
December 2021. Engineers prepare for one of the most important space launches in a generation.
Standing by for terminal count.
The launch site, along the equator in South America, allows for the shortest possible flight into orbit.
10, 9, 8, 7, 6, 5, 4.
The rocket's payload, tucked into a metal cocoon on its nose, will travel much further.
And we have engine start. And liftoff.
Décollage.
Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
After 20 years in development and decades more in the planning, the James Webb Space Telescope is on its way. It is one of the most complex engineering projects ever undertaken, not only in the technology it will use to observe the universe, but in the precision needed to place it into its final position.
Punching a hole through the clouds, 20 seconds into the flight, good pitch program reported.
The rocket reaches orbit and releases its payload. The telescope will now travel to a location 1.5 million kilometers away, 4 times the distance from Earth to the Moon. There, the James Webb will build on the pioneer. In a continuous stream of images and data captured over 3 decades, Hubble has revolutionized our understanding of the universe. The primary mirror on the James Webb has 6 times the light-gathering power of Hubble's. Its 18 gold segments were designed to be folded up to fit into a rocket. Once deployed in the cold reaches of interplanetary space, they will act as one to see objects once thought beyond the limits of our vision. Scientists will use Webb to explore some of the most important questions in science. How did the universe as we know it take shape? What events gave rise to galaxies, solar systems, and planets like ours? Answering these questions has been a central quest of modern astronomy for over a century. Using the new state-of-the-art Hooker telescope above Pasadena, California back in the 1920s, the astronomer Edwin Hubble examined distant galaxies all around the sky. He found that the light of these galaxies is shifted to the red end of the light spectrum, much like the sound of a train that changes pitch as it passes and moves away. means the universe at large is expanding in every direction. Scientists concluded that the universe must have originated at a single moment in time, in an explosive event that came to be known as the Big Bang. Because of the time it takes the light of distant objects to reach us, the farther out into space we look, the farther back in time we see. The story of how the universe evolved from its early days has come together in theories tested in countless telescope observations and in computer simulations of galaxies growing, merging to form larger galaxies, and becoming part of a vast spider's web structure of gas and galaxies sculpted by the relentless workings of gravity. To understand the physics that drove cosmic evolution, scientists have built giant laboratories to explore fundamental properties of matter and energy. By colliding atoms at nearly the speed of light, they can recreate the energy states and chemical composition of the universe in its infancy. But our information about the primordial universe is far from complete. With the launch of the James Webb Space Telescope, we may finally be able to see into those early times. The instruments were designed to glimpse an era when the first stars and galaxies formed, and to document the events and forces that brought the universe to life. First, Webb would have to reach its final position. To avoid overheating in the bright sunlight of interplanetary space, the spacecraft performs a series of gentle rolls. Near the end of powered flight, the roll sequence stops, and the telescope separates from the launcher. Webb continues its journey under its own power. Along the way, scientists on Earth direct the observatory through a series of deployments. First, the solar array. From now on, its electrical power needs will be supplied by the sun. The high-gain antenna drops down for communication back to the mothership, planet Earth. Next, the two sun shields drop slowly into position. The tower, holding the telescope mirrors and all mission instruments, rises up from its base. A metallic flap drops down to help balance pressure from sunlight around the telescope's center of mass. Protective covers roll back from the folded sun shields. Booms extend and pull them out to their hexagonal shape, the size of a tennis court. It's now time to tension the sun shield membranes, each thinner than a human hair. When these layers are finally stretched and separated, they'll allow the telescope to cool down to -200 degrees Celsius, cold enough to liquefy air. The secondary mirror extends into position and latches firmly in place. Then, a radiator to release excess heat away from the telescope. Finally, the remaining mirror segments folded back for the journey through Earth's atmosphere. It's now 29 days after launch. A course correction puts Webb into a halo orbit around the Sun-Earth L2 point, where its journey around the Sun is synchronized with the gravity of Earth. Out here, the telescope is free from all thermal influences from our planet. Its sun shields block light from the Sun, Earth, and Moon, the brightest objects in the sky. Scientists now ready the observatory for operation by aligning each of its mirrors into its correct final position. With sensors focusing on the infrared part of the light spectrum, this telescope can capture photons that move through dust that permeates the universe and obscures our view. Webb's long-awaited first images show its promise. Here is exquisite detail on the edges of the Carinae Nebula. These images show the fine sculpting of gas by hot winds emitted by resident stars. Here is a Hubble image of NGC 628, the so-called phantom galaxy, in optical light. Here's how Webb sees it in the infrared, with its bright pockets of starbirth and dramatic spiral structure. Stephan's Quintet, a photogenic group of 5 galaxies in the northern constellation of Pegasus. 4 of them are gravitationally bound to each other in one of the best-studied compact galaxy groups. Using Webb's spectrograph to analyze the light of one-member galaxy, called NGC 7319, astronomers identified the distinctive chemical makeup of gas swirling around a supermassive black hole in its core. Finally, here's Webb's first deep image, a galaxy cluster called SMACS 0723, 4.6 billion light-years away. The immense gravity of the cluster acts as a lens, magnifying galaxies billions of light-years beyond it. They appear as arcs of light encircling the cluster. A series of faint smudges identified in this image smash Hubble's previous record for the most distant galaxy ever recorded. Their light comes from around 300 million years after the Big Bang. These distant galaxies are messengers from a time when our universe was in its infancy, still without visible form, yet poised to burst forth. Faint signal we call the cosmic microwave background. From there, the universe faded into a period of darkness, the so-called cosmic dark ages, lasting hundreds of millions of years. In time, the universe lit up again, thanks to one of the most extraordinary chain of events since the Big Bang itself, a cosmic 1-2 punch that only the James Webb Space Telescope is able to see. A supercomputer model visualizes those events beginning just 6 million years after the Big Bang. In the darkness, gravity draws an unseen presence astronomers call dark matter into diffuse halos. Within them, clouds of hydrogen gas form, becoming more and more dense over time. As gravity compresses these clouds, they begin to heat up, then finally ignite to form the first generation of stars. These stars are giants, much larger than any today. They burn hot and fast, with some ending their lives in powerful supernovae that will transform the young universe. The supernova litters its surroundings with heavier elements generated in the explosion: carbon, silicon, iron, and more. These so-called metals cause surrounding clouds of hydrogen to cool, which allows them to collapse. Turbulence breaks them into smaller pockets. A cluster of smaller stars now begins to form. The first stars not only paved the way. As these stars exploded, massive clouds of hydrogen gas collapsed into their cores, giving rise to the first generation of black holes. These ultra-dense objects grew larger on a diet of gas and small stars, becoming gravitational focal points for the birth of the first galaxies. As these primordial star systems grew, their rising gravity attracted others. The largest ones merged and collided, growing larger still. This had the effect of force-feeding the black holes that lurked in their cores. As these black holes swallowed huge volumes of gas, they generated powerful blast waves that slowed the inrush of gas, countering the effects of gravity. Stars, too, joined in this battle against gravity. You can see it playing out in this wider view of a time almost 400 million years later. The gravity of dark matter has already drawn the universe into a vast web. Stars are being born where filaments of gas, shown in blue, come together. Ultraviolet light from these stars begins to strip electrons from hydrogen atoms in a process called ionization. That causes surrounding regions to glow with visible light. Here, the ionized gas appears as bubbles. They are associated with pockets of elevated temperatures, shown in red. As well as high concentrations of metals spread by supernovae, shown in green. Heating from ionization pushes the gas out and suppresses the rate of starbirth. The spread of metals created in supernovae allows pockets of gas to cool and fall inward, increasing the rate of starbirth. This push of energy and pull of gravity turned the universe into a mix of hot and cold regions, large and small star clusters, and pockets of gas amid clouds of dust rich in metals. We now advance the clock to about 1 billion years after the Big Bang. In this era, stars are being born at a blistering pace, and black holes are actively gobbling up their surroundings. Galaxies are merging, forming a chain of dense clusters. The heating slows the flow of gas into the clusters, limiting their growth. That allows smaller galaxies like ours to form on the margins. The Hubble Space Telescope was at the center of what astronomers call the golden age of orbital and multi-wavelength astronomy. The launch of the James Webb Space Telescope promises to spark a whole new era of discovery. Astronomers will enhance their view into the deep universe by combining Webb observations with those of new generation ground telescopes, like the giant extra-large telescope in Chile, whose extraordinary light-gathering power allows it to zero in on primitive galaxies identified by Webb, or the wide-angle view of its neighbor, the Vera Rubin telescope. It is designed to pick up stellar explosions or black hole collisions in almost every direction. All eyes will be on the images and data streaming in from the next great observatory in space, the James Webb. The world awaits a new generation of discoveries expected of this marvel of engineering and imagination.